So this is a problem about a man whose mass is 85 kilograms, and he's trying to pull a plane, and that plane has a mass of 109,000 kilograms. He's pulling it with a rope, so we expect there's going to be some sort of tension in that rope, and he's relying on the fact that the tarmac under his feet has a coefficient of static friction of 0.77. But the plane, because it's on some wheels, we're sort of going to ignore the friction between the wheels and the tarmac, and we're just going to think of it as frictionless. Okay, that's what the problem is saying. And then the question really is, what is the acceleration of the plane and the person? I mean, they're both moving with the same acceleration. If this rope is really transferring the tension properly, then they're both going to be moving with the same acceleration. Okay, so the first thing I'm thinking is I could draw the free body diagram of the person, but I could also just figure out the force that is moving this person forward. And the only way this person is going to move forward is if there is friction with the tarmac, because otherwise his feet would just keep slipping and he would never move forward. So I can just look at that part. I can just enlarge this piece and look at his feet. And, I'm going to think of it this way. There's his foot, and he's trying to move against the tarmac. And he is trying to move backwards. So his motion is towards the back. The motion of his foot is towards the back. So that means that the static friction, the friction force from the tarmac on his foot, is going to be in the opposite. It's going to oppose the motion. Okay? And that makes sense because otherwise he would never move forward if there was no force towards the forward direction. Okay? So how do I figure out this force? I need to figure out what the normal force is, because the friction force is always the static friction coefficient, the maximum one in this case, because he's going to start moving, and this is multiplied by the normal force. So how do I figure out the normal force? So I look at the free body diagram for the person, and I know that he has some mass, so he's going to have a weight, which is the pull of gravity, the pull of Earth on his body, and this is going to be his mass multiplied by the acceleration of gravity. And the normal force then is going to be the response to this push on the ground, and that is going to be perpendicular to the tarmac. It's going to be straight up, and this is going to be the normal force. And in this case, because there is no movement in y, I can figure out right away that this is also equal to this. It has the same magnitude as the weight and in the opposite direction. So it's also equal to the mass of the man multiplied by the acceleration of gravity. And in this case, then the static friction is going to be equal to the static friction coefficient multiplied by this force, which is the mass of the man multiplied by g. The other thing that is acting on the man, of course, is the tension from the rope. Okay? So I could solve this. I could basically say the man is moving in this direction with some acceleration a. So I can figure out that in the x direction, I can look at the net force in the x direction, and I can equate that to the mass of the man multiplied by the acceleration. And I could do the same thing for the plane, and from that I can figure out the acceleration. Or I could look at, now this is the driving force for the whole system. So I can calculate the acceleration knowing that force that is driving the whole system right away. So let's do it both ways and see if we get the same answer. So if I'm doing it this way with the free body diagrams of both the man and the plane, then I can solve this free body diagram. I've already solved the y part. I've equated the magnitudes of these two forces. In the x direction, then I could say that the net force is equal to the mass of the man multiplied by the acceleration of the man. the net force in the x direction is going to be whatever is in the positive, which is the static force, and whatever's in the negative x direction gets a negative. So I've decided this is my positive x and this is my positive y. So in the positive x direction, I have the static force. In the negative x direction, and I have the tension force. And I know that this is going to be equal to the mass of the man multiplied by the acceleration. Now, I don't know the acceleration and I don't know the tension. So this equation is not going to help me find both. So I need another equation, and the other equation is going to come from analyzing the free body diagram of the airplane. The free body diagram of the airplane looks like this. It has some weight, which is going to be equal to its mass, which I'm going to label with capital M to differentiate from the mass of the man. And of course, there's going to be a normal force, which of course is always is in this case going to be equal to the weight, but opposite in direction. But that doesn't really take us anywhere, because what we care about is the x really. And in this case, the rope is pulling on the plane in this direction, so this is going to be the tension in the rope, and of course it's equal to the same tension in the rope on the other side, because the rope is transmitting the tension faithfully. So if I want then to write the equation of motion, I have to think about what is the acceleration of the plane. And like I said, the acceleration of the man and the acceleration of the plane are going to be the same, so I'm not going to label them differently. I'm just going to label them as A. And in this case, if I'm writing the net force in the x direction, that's just the tension, because there is no friction for the plane, like we said before. So the tension then is going to be the net force, and that is going to be equal to the mass times the acceleration, but in this case, the mass is the big M, which is the mass of the plane multiplied by the acceleration of the plane, which is the same as the other acceleration. So that says that T is equal to capital M times A, and that's equation 2. Now, I still don't know T, I still don't know A. But now I have two equations in T and A, so I can solve these two. What I really don't care about is the tension. I care about the acceleration. If I was asked about the tension, then I will solve this differently. But now, because I'm asked about the acceleration, I want to eliminate T from both equations. So I can just take whatever value for T here, and I put it in this equation here, substitute. Or the other way you could do it is you could say, you know what, I'm adding the two equations, 1 plus 2. I notice that on the left-hand side, T here has a positive sign, and on the left-hand side here, T has a negative sign. So I'm just going to add the two equations. So I'm going to say 1 plus 2, equation 1 plus equation 2, which means I add the left-hand sides and I add the right-hand sides. So the left-hand side is going to be T plus mu s mg minus T. So that's both left-hand sides added is equal to both right-hand sides added, M, capital MA plus small ma. The T cancels with the T, and I'm left with the friction force is equal to, so mu s mg is equal to capital M plus small m multiplied by the acceleration, which implies that the acceleration is equal to this force divided by the total mass. And I can sub in the numbers by saying 0.77 multiplied by the mass of the man, which is 85 kilograms, multiplied by the acceleration due to gravity, divided by the sum of the masses, which is 109,085. This is equal to 5.88 times 10 to the minus 3 meter per second squared. Now, like I told you, there's another way of solving this problem without having to do both free body diagrams. I could have just looked at what happens to the foot of the man and figured out the friction force, and then I could have deduced that the friction force is really the only force that is moving the system forward. Okay, so if I treat the man and the plane together as a system now, the only force that is moving them forward is this friction force. So I could have said right away that the friction force is equal to the mass of the system multiplied by their acceleration, which means that the acceleration is equal to the friction force divided by the mass of the system. And the friction force I figured out is the coefficient of static friction multiplied by the mass of the man multiplied by g, and that's divided by m plus m, and that's going to give me the same answer